Okay, let's look at the Doppler effect, which is probably something you've experienced or seen or whatever. When the source of a sound is moving, then the observer perceives a frequency uh, that is different from the actual frequency. Remember, when I say frequency here, I'm referring to the pitch of the sound. That's different from the actual frequency. So, for example, if you have a truck or a police car, and they're coming towards you, they are emitting a sound. And let's say that the frequency here, we'll call it F1. And you're standing over here, you're going to experience a frequency, you're going to observe a frequency, I'll call this F2, that is bigger than F1. It'll sound higher. Think about a police car coming towards you. You can really experience this coming towards you and then moving away from you. Or if you want to hear like a train whistle, you can click a little link here. I'll have a train where you can hear the Doppler shift of the train as it comes towards you. Likewise, if the car is moving away from you, then it will have a lower pitch or a lower frequency than its actual. Now, if the source, or for when the source is moving, which is the most common case when the source is moving, our observed frequency, that's the frequency that it appears to us, is equal to the frequency of the source, that's the actual frequency, times the velocity of the wave divided by the velocity of the wave plus or minus the velocity of the source. And you might be wondering, well, gosh, why does it have this plus or minus? Well, that's whether it's moving towards or away. And gosh, you know what? I always, oops, sorry, oh, there's my kids. I always get these mixed up. I forget which is which. So I just imagine, well, gosh, if I'm moving towards, that means that the f obs, the observed frequency, is bigger than f of the source. And if that's bigger, then that means in the denominator I must have VW minus VS. So if I'm moving towards, then I subtract because that makes this smaller, which makes this fraction to be greater than 1, which causes my f-obs to be bigger than the source. So just think about this, whether you use the plus or the minus. But if I'm moving towards, I use the minus. If I'm moving away from, I use the positive. And that way, this becomes bigger than the numerator, and it becomes a fraction that's less than 1. And so f-obs would then be less than f of the source. So you'll have this equation on your equation sheet, but when you encounter the problems on the test or in the homework, and there are a couple of problems in the homework, then just think about what do I use, plus or minus. Also, when the observer is moving, we get a very similar equation. We get frequency of the source times VW plus or minus VS divided by VW, where VW is the speed of the wave. Most of the time, that's going to be the speed of sound in air, and that will be provided to you. It's like 340. And similarly here, you think about, do I use plus or minus? And you think about, well, gosh, is f obs bigger than or less than f of the source? And so, for example, if the observer is moving towards the source, then the observed frequency will be bigger than the actual frequency in exactly the same way. So if you're holding a buzzing thing and you run towards someone, the frequency will appear higher. And if f-obs is bigger than the actual frequency, which is our fs, by the way, then that means that I'm going to have VW plus VS in the numerator here, because that gives me an observed frequency that's bigger than the source frequency. If I'm moving away, then I use negative. So just think about how to use those positive or negative signs. Now, a sonic boom occurs when the speed of the source exceeds, actually, a better way to think about this is that it approaches and maybe it exceeds the speed of sound a little bit, but when it exceeds the speed of the wave, or approaches the speed of the wave. Listen, think about a boat. A boat traveling through water, it produces waves that follow behind it. These waves have a certain wave speed. That's their VW. They have a certain wave speed, so they will travel through the water depending upon the depth and the temperature and the density of the water. They have a particular speed at which they travel through the water that's dependent upon the medium. But if the boat produces these waves at a rate that's too fast, then these waves are all going to sort of collect up. And what you're going to get is this construct of interference wherein the peaks and the peaks will line up, the troughs and the troughs will line up, and you'll get a really big wave. And the same thing happens with airplanes, a very similar thing. When they exceed the speed of sound, then the sound that they're producing uh, basically catches up with itself because they're going so fast. They produce this sound wave, and then they produce another sound wave, and another sound wave, and another sound wave, and they just all bunch up together. And they produce this sonic boom, which you may have heard. Fighter jets often do this. So if you've ever seen the Blue Angels or the Air Force equivalent or whatever, uh, if they go at a certain speed that approaches the speed of sound, then they'll produce this loud boom, which is a sonic boom. I have a video here. It's not my video, but you know, it's on the internet. So you can take a look at that if you like.